Module 2 is module about graphing fundamentals. So we will discuss various main graph features. We will talk about how to sketch something from a table of values, what are intercepts and their algebraic meaning, as well as we will consider several types of functions, including piecewise functions. This module really should be a precursor to module 3, which is all about functions. So I encourage you to do it back to back in that order. Let's take a look at the first example of simply developing some visual understanding of what graphs are. Amanda fills in a bathtub, gets in, relaxes for 30 minutes, gets out, and drains the water. We would like to sketch how the height of the water varies over time, and then also how the volume of the water varies over time. So let's start with the first graph of the height of the water varying over time. So our vertical axis will correspond to the height of the water, whereas our horizontal axis will correspond to the time. And let us label those as that. So what is happening? We have to go through the description and see what are the different stages of the function or of the graph here. So first of all, Amanda fills in the tub. So as the tub gets full and full with water, the height of the water increases up until where the tub is full, or what Amanda considers to be full enough to get in. Then the tub stays at that level for a couple of minutes, let's say, up until Amanda decides to get into the tub. And once Amanda gets in the tub, the height of the water in the tub, of course, increases just a little bit, right? So this is when Amanda gets in. Then she relaxes in the tub for some amount of time. So let's say this, and let's suppose that this will be 30 minutes. The next thing that happens is that she gets out and then drains the tub. So essentially the inverse processes of the first two steps here. So she gets out, there's maybe some time delay in her draining the tub, and then she drains the tub. Okay, we have some intuitive understanding of graphs in terms of what it means to be increasing and what it means to stay constant that are highlighted here. Let's take a look at now how to sketch the graph of the exact same scenario, but in terms of volume of the water. So here, the vertical axis will correspond to the volume of the water, whereas the horizontal one will continue to be playing the role of time. So what happened here is the volume of the water was in the tub was obviously increasing as the tub was getting full. So let's say at this point, the tub is full. But now notice that here when Amanda got in, the height of the water increased, while when Amanda gets in, the volume of the water isn't actually going to increase. So for the whole time between filling up the tub and draining the tub, so 30-something minutes, the volume of the water stays the same. And then when Amanda gets out and drains the tub, the volume of the water decreases. Okay, so notice the subtle differences here once again in the height and the volume of the water, one having a particular little kink in here and one not. So the constant levels between these two graphs are different depending on the content. Now, the issue with these two graphs is the fact that, for example, notice how I didn't introduce any scales because we were not actually told enough information to introduce scales. We did not know how much time there was between filling up the tub and getting in. All we knew that there were 30 minutes when Amanda actually just relaxes in the tub. So this was the only indication of the scale. Introducing a coordinate system and being more careful with how we sketch the graphs will, of course, provide more information about the graph and more information about the situation. These weren't really graphs as much as they were sketches that were representing the situation. So what happens when we introduce a coordinate system and try to think of the graphs in a more precise manner? So let's say this is a graph of some function given below. I'm going to take for granted here that we have some understanding of what a function is. Again, this is what Module 3 is going to focus on. Here, we're just thinking in terms of big graph features. We're asked to list x and y intercepts, as well as determine the intervals where the graph is positive, negative, increasing, and decreasing. A lot of these things are, once again, intuitively understood from the graph, so let's just try to read them off the graph. So first of all, x and y intercepts. Let's start with x intercepts. X intercepts are where the graph crosses the x-axis. So in this case, it will be these 3 points. So first of all, let's write a description. X-intercept is where the graph crosses the x-axis. And in this case, it will cross it in 3 different spots. Looking at these 3 points, what do they have in common? Their x-coordinates are different, but they all have a y-coordinate of 0. And this is how we generally will actually find x-intercepts. X-intercept is when the y-coordinate is equal to 0. So in this case, we have 3 of them, and they occur at x equals -2, at x equals 1, and at x equals 5. For y-intercepts, if the graph is that of a function, then you should remember from precalculus that a function should pass a vertical line test, which means that any vertical line will intersect the graph at most once. A y-intercept or y-axis is just one of the vertical lines. So if the graph is that of a function, we're not going to have y-intercepts, but we will have y-intercept. And that is when the graph crosses y-axis. Now, this is the reverse situation. The graph crosses the y-axis when the x-coordinate is 0, and that is how we will find our y-intercepts. Okay, and in this case, we do have 1, and it's at y equals 2. Excellent. The next are the intervals where the function is positive and negative. Let's talk about positive first. What does it mean for a function to be positive? A function is the y values given some value of x. So positive means for y values, and the y values are positive. This is the y values of 0. Those are our x-intercepts. So positive y values will mean anything above the x-axis. Above x-axis. Okay, and so now we can look at when does that happen? When does this graph lie above the x-axis? Well, it happens for this piece of the graph here and for this piece of the graph here. So using the interval notation, we can say that this happens between -2 and 1 for x's, right? Between -2 and 1, and then between 5 and forever. So union from 5 to infinity. Okay, so this is for positive. What about for when is the graph negative? The opposite of that. Negative, again, this means in terms of y values, will then correspond to below x-axis. Okay, so in this direction. And then, of course, this happens for this particular graph here. This is when it's below the x-axis, and here. And in terms of the interval notation, we then have to say that it's from -infinity up until -2, and then between these 2 points, so between 1 and 5. Okay, so this will be our 2 regions, from -infinity to -2, union from 1 to 5. Okay, so let me note this on the graph once again, that above the x-axis means positive, and below the x-axis means negative in terms of y values of the graph. And then the last thing we're asked to consider here is to talk about the intervals when the graph is increasing and decreasing. For that, it is useful to imagine that you are hiking on this graph. Increasing will correspond to when you're walking up the hill, and decreasing will correspond to when you're walking down the hill. Okay, so increasing, let me say uphill. So in this case, that corresponds to the graph portion up until this peak here, and then starting from this lowest point, moving upwards in this direction. So again, in terms of the interval notation for the x, that means that I'm coming from all the negative values and up until this peak here, so approximately minus 1.5 for x here, and to this point here. So let's say that this is approximately 3.5. Okay, so these are an approximation. I'm just eyeballing from the graph. So increasing from negative infinity to minus 1.5, and then again from 3.5 to positive infinity. Whereas decreasing will correspond to walking downhill on the graph. And then, of course, will correspond to the two other portions. So when we're walking down the hill on the graph, this will be from this point downhill to this point right here. So between negative 1.5 and positive 3.5. Notice how you can probably include these points as well. This point right on the top, if you're standing right on top of this peak, you're neither walking up the hill or down the hill, so you can choose to include that point or not. Okay, these are how one would describe these main features of the graph. So keep that in mind as we're going to go and talk later about calculus tools. Here, the graph of a function was given to us, but the function expression, what this meant algebraically, was not. So let's take a look at the next example, where we are given an analytical version or formulaic version of the function, and we're asked to sketch the graph of it. It is extremely important to understand what is the relationship between a function formula and the graph of it is. The graph of the function is the set of points which satisfy the equation of the function. So the points you're going to draw on the graph are exactly the points that make this equation true. Now, it is often easier to start graph if you don't know what the shape looks like at all. The easiest way to do to graph anything is to actually just start a table of values. Find some points that belong in the graph and sketch them on the coordinate system to have some idea of where they go. Okay, so you can start with any points and you can produce a table of values corresponding to any points, but in keeping with the spirit of what we've discussed above, let's maybe start by finding the x and the y intercept of this function. So for the x-intercept, as discussed above, we will set y to be 0, which is our f of x, which in this case will give us x squared minus x minus 6 is equal to 0. To solve this equation, the easiest thing to do in this case is to factor it out. So I will get x minus 3, x plus 2, and this has to equal to 0. Factoring works because now we've managed to come up with a product of two things that's equal to 0. The only way that a product is ever 0 is if one of the factors is 0. So this immediately gives us either x is equal to 3 or x is equal to negative 2. And those are going to be our x-intercepts. So let's put together a starting graph of a function here and put the points that we already know belong on the graph of this function. So my x and y intercept is negative 2 and positive 3. So I know that these 2 points are indeed on my graph. The other thing I can find is to find the y-intercepts. And of course, for that, I have to set x to be 0. And this is the easy part. I set x to be 0 in this equation. I'm going to get 0 squared. Let me write this out. 0 squared minus 0 minus 6. So I'm going to get minus 6, which means that my y-intercept is at negative 6. So my function goes through this point right here. Okay, now, again, coming back to what it actually means to have a graph of a function, let me just point out once again that points on the graph actually correspond or represent pairs x, y that satisfy the equation of the function, so that make y equals x squared minus x minus 6 true. This is why constructing a table of values is such an easy thing to do, because I simply have to plug in some x values, calculate the y value depending on that, and I'm going to get the xy points to put on my graph. Now, it is completely up to you how many points you're going to include in your table of values, but I strongly recommend coming up with a variety of points. So don't discriminate against negative numbers. Plug in some negative numbers to see what happens, right? So for example, let's plug in -3. If I plug in -3 into this equation, same as this equation, so -3 all squared minus -3 minus 6. Doing the calculations, I'm going to get 6. If I plug in -2, notice that -2 is one of my x-intercepts. If I plug in -2 into this equation right here, again, doing the math, -2 squared minus -2 minus 6, I will not surprisingly get a 0. If I plug in -1, I'm going to get -4. If I plug in a 0, I'm going to get -6, as also indicated by our y-intercept. And now let me plug in some positive numbers here. So if I plug in, let's say 1, 2, and 3, correspondingly, I'm going to get -6, -4, and 0 once again, because 3 is my other x-intercept. Now I actually have a whole bunch of points to work with, so I can put them all on the graph as pairs. My first point is x is -3, so this guy right here, and y is going to be 6. 1, 2, 3, 4, 5, 6. So I have a point up here. The next point that satisfies the equation is -2, 0. So I already have that. The next one is -1, -4. So this point right here. -1, -4 is this guy. 0, 6 I already have on the graph. The next one in my table of values is 1, 6. There we go. So this is my 1, -6. 2 and -4. 2 and -4 right there. 3 and 0 is the point that I already have. Now, generally, the more points you have for the graph of your function, the better. Here, as we will discuss in later modules, this is a quadratic function. Its graph is going to be a parabola, so we can simply smoothly connect all the points that we already have constructed to come up with the graph of a reasonable parabola here. There we go. Something like that. Let's pretend it's all symmetric. Let's discuss a couple of really important points about this graph. In particular, the fact that these x-intercepts were exactly the solution to the function equation being equal to 0. So x-intercepts are solutions to the equation being equal to 0. So the solutions to f of x equals to 0. This is why x-intercepts are also called zeros of a function, because they are in fact what make the function equal to 0. And they're also sometimes called roots of the function. All of these words stand for the exact same thing. One of them has a clearly more geometrical or graphical meaning, but they all actually represent the exact same thing, and algebraically they correspond to when the function is equal to 0. This is the one very important point here. You can think of all of these questions in terms of x and y-intercept intervals where the function is positive, negative, increasing, and decreasing for this function as well. And I encourage you to list those properties of this graph as a further exercise to this particular topic. Let's take a look at some other graphs and hopefully some very familiar graphs of power functions and their transformations. So power functions are just functions of the form x to some power, where that power is a nice integer, positive integer. Okay, let's start by sketching the graphs of the functions x squared, x cubed, x to the fourth, and so on. So starting with x squared, I know that you know what a familiar shape it would be, but let's go through and notice some actual things of when we plug in numbers into these functions. So y equals x squared versus, let's say, y equals x cubed. Okay, so for y equals x squared, again, you can remember from pre-calculus, hopefully, that this will represent simply a parabola. But how does one obtain that parabola? And that is, again, by the fact that a graph of a function is a set of points that satisfy this equation of the function. I am free to pick my x's, that's why they're called independent variable, and then this equation will give me the corresponding y's. So if my x is 0, then y is 0, which gives me the fact that it goes through the origin. If x is 1, then I'm going to get the point of 1 squared. If x is minus 1, I'm still going to get a point of 1, because anything squared is a positive value, and so on. So constructing these values will indeed produce a nice, smooth graph of a parabola. For the case of y equals x cubed, 0 cubed is still 0, so this is still going through the origin, and in fact any of these functions will go through the origin because 0 to any power is still just 0, and also any of these functions will go through the point 1, 1, because 1 to any power is just 1. Negative 1, though, cubed, will give me a negative 1. So in this case, I'm going to lie on the negative side, and we will notice that the general function graph of a cubic polynomial will look like this snaky cubic shape. Okay? Now, what if we were to think about higher power graphs, so x to the 4th or x to the 5th? It doesn't take very long to realize that x to the 4th will have a shape that looks like the quadratic or, parabola function, whereas x to the 5th will look like the shape of a cubic or whatever, this wiggly, snaky shape of a function, right? Just think about the numbers. If I plug in into x to the 4th, 1 to the 4th, I'm going to get 1. Negative 1, I'm still going to get 1. So I'm still going to get this exactly symmetric parabola shape, whereas x to the 5th, negative numbers will remain negative, while positive will stay positive. So I'm going to get this shape where the graph belongs to the first and the third quadrant. Now, the next question that I would like to ask is, well, this actually generalizes, maybe let me just make first a note that what we've just talked about generalizes to the fact that all of the even power functions will look like parabolas, while all the all powered functions will look like the cubic shape. But how would they actually correspond to each other on the same graph? So if I wanted to, instead of drawing them on separate graphs, draw them all on the same graph, what kind of relationships would I be seeing? So this is where it's helpful to take a minute and, again, plug in the numbers just to get a number sense of this. So if I am thinking of, let's say, 1/2 squared, 1/2 cubed, 1/2 to the 4th, versus something like 2 squared and 2 cubed and 2 to the 4th, we will notice quite quickly, and if you're not comfortable with exponents and exponential rules, please review the previous module 1 on the various exponential laws. This will give me a quarter, an eighth, 1/16, where this will give me 4th, 4, 8, and 16. So what we notice here is that the higher the power of a fraction, the smaller the fraction. So raising a fraction to a higher power makes it smaller, whereas raising a number to the higher power makes the number bigger. Okay, and this observation is at the core of how we can draw the power functions on the same graph. So if I have a graph of x squared, this nice parabola here, then if I were to next on the same graph draw the graph of x cubed, I will notice that for small numbers, I have to be lower than the parabola. So for small numbers, for the cubic, it's actually lower than the parabola, but then for larger numbers, it's above the parabola. So at some point, a switch happens, and my cubic will grow faster over there. If I were now to, on the same graph, draw the degree 4 power function, once again, I notice that the degree 4, for small numbers, for fractions less than 1 in this case, the number is even smaller. So that means that my degree 4 is going to be even flatter near the origin still, But then once I've passed the point 1, and I'm actually raising large numbers to large powers, my numbers will grow faster. So degree 4 polynomial will be flatter at the origin, but will surpass my parabola growth later. Now I'm drawing this all by hand, so this is not by any means a very accurate representation of it. This is pretty good, except for it really should look symmetric on both sides, and the graphs should be a little bit neater. So keep that in mind, okay? With this in mind, in fact, let's take a look at how would a software draw these functions. Desmos is an excellent online graphing calculator that is completely free. So I strongly encourage you to take good use of this tool. So let's try to graph the functions that we had. This is x squared. How about x cubed? This is our familiar shape for x cubed, x to the 4th, and maybe let's throw in x to the 5th into the mix as well. Let me zoom in and show you what's happening, right? So as we go through, this is x squared. The next graph is x cubed. So notice that it's flatter near the origin than x squared, but then past 1, 1, it surpasses the x squared graph and starts growing faster. If I draw x to the 4th, it's flatter still at the beginning, but then grows faster past a certain point. X to the 5th is the flattest yet, but then once 1, 1 gets surpassed, it grows the fastest afterwards, right? If I continue with these functions, we will continue seeing the exact same pattern. So overall, the functions, the higher the degree, the flatter it looks like near the origin, but then the faster it grows once it passes a certain point, in this case 1. Now these guys all had just x to some power. What about some kinds of transformations on these functions? So for example, here we just take x squared and change up the coefficient in front of it. 3, 1/2, minus 2. Once again, your previous calculus experience should suggest what these functions look like. But if you're struggling a little bit, plug in some numbers and you will see what that actually corresponds to, what kind of transformations these actually correspond to. So normally I will start with the base graph of x squared. So let's say this is x squared. If the number in front of it, if the coefficient is bigger than 1, then this will correspond to a stretch. So 3x squared will be the same parabola as before, but now stretched out. Okay, so the parabola shape will remain, but now it's going to look a little bit stretched or squished. So if the number in front is less than 1, it's going to correspond to horizontal compression. So it's going to be the same parabola shape, but now shallower and wider. So this will be a 1/2 x squared, whereas the minus corresponds to the flip in the x-axis. Okay, so minus 2x squared will then correspond to a function down here. So something like this, minus 2x squared. So generally, the change of the coefficient corresponds to a, a stretch factor. Okay, what if we now take a look at these two graphs? X squared plus 3, x squared minus 4. So notice that plus 3 occurs outside of x squared here, which means that x's are not really affected by it. Whatever the shape of x squared was, we're now just adding plus 3 to it sort of on the outside. So this means that the plus 3 and minus 4 in this case actually simply correspond to a vertical shift. So if this is my original function x squared, then x squared plus 3 is going to be the exact same function, but moved 3 units up, because only the y-coordinate got affected. And x squared minus 4 will correspond to the exact same function, but moved down. Maybe I should make it look more like the same function. It hasn't been stretched vertically or horizontally in any way. It's still just x squared minus 4. So adding things onto the outside of your base function will correspond to a vertical shift. And then finally, the last transformation here is x plus 3 all squared. and then x minus 4 all squared. So this is noticeably different from the case before. So notice how plus 3 here was added onto the outside of x squared. Here, the entire function is squared, and x has actually been affected by this 3 and this negative 4. So in this case, what we end up having is a horizontal shift. Now this one seems always a little bit backwards. So let's start with the graph of parabola y equals x squared. And the way to think about this, there's a couple of ways to think about this. Let me maybe name two. So this will be the same parabola shaped because it's a square. And the way you can discover whether it's a shift to the left or to the right is just to plug in one point, preferably, or try to find out, for example, where is now this vertex? Is it to the left or is it to the right? Okay, so what would make this equation 0 now? And it will make it 0 if x in this case is negative 3. So then my point will correspond to minus 3 on this side. The other way to think about this is to think that nothing really changed in terms of the parabola. It's actually the x-axis that got shifted. So the origin is here, or this is where the origin would be the vertex of the parabola, right? And so my parabola shifted 3 to the left with respect to the origin. Okay, so this guy will now be x plus 3 all squared, whereas thinking about this one, again, I find that it's easier to actually think about when is this going to be 0, and then finding that point, and then realizing whether it's to the left or to the right. The thing that will make the inside 0 here is x value being 4, which means that now my vertex of the parabola has to happen at x equals 4, which means that this shift corresponds to the entire function being shifted to the right. Okay, so overall, this internal addition or subtraction corresponds to horizontal shift. These types of transformations you can apply to any function, doesn't just have to be x squared. So try to go through the exact same example, but with x cubed all over the place. So cubic function here and there, just to see how transformations work on that function. This will generalize in the most natural ways to all the functions. In terms of sketching power functions on the same sketch and then somehow relating them, their points of intersection to their algebraic meaning, let's take a look at this example here. We're asked to sketch 3x to the 4th and 5x to the 7th, and then find the points of intersection. So let's start by sketching the two functions. First, it's going to be a true sketch. I'm not going to put the scale on it right away. I'm really just after qualitative shapes of these functions. So 3x to the 4th, we've just discovered that the coefficient in front, this 3, will correspond to a vertical stretch. So I'm really looking for the shape of the function x to the 4th, which is even. So it's going to have this parabola shape, and it's going to be stretched out by a factor of 3. Okay, but the general shape will be that of a parabola. So something like this. I'm not sketching the I'm not writing down these scales, so I don't have to be particularly mindful of exact points that it has to go through. I just know it has to have a general parabola shape. Excellent. Now, this next guy here, what kind of general shape will that have? Well, the power function here is x to the 7th, and it has a stretch factor of 5. X to the 7th, that's x to an odd power, so it will have a general snaky or cubic shape, and then it will be stretched out by a factor of 5. Now, going back to our discussion of how the power functions work with each other, remember that the higher the power, the flatter the function is near the origin, and then the faster it grows after. So at some point, this switch has to happen. So if I'm drawing x to the 4th versus x to the 7th, 7 is bigger than 4, which means that near the origin, my x to the 7th will be flatter, closer to the x-axis, and then at some point, it will start growing faster, right? So somewhere along the way, a switch happened, and then it's a general shape of a cubic function, so it had to go in this snaky shape and into the negatives here. So purely by sketching, I already notice that I do have 2 points of intersection here and there. How do I find them? Well, notice that at both of these points, I have that the functions actually have the same x values and the same y values, right? So that means that in order to find points of intersection, I simply need to set functions to be equal to each other in terms of their y coordinates. Okay, so we have this equation here. If you're struggling to remember how to solve equations of this type and not lose roots and just how to be generally very careful about solving equations, please take a look at the previous module, Module 1, for a general discussion on solving equations. So in this case, I'm going to move everything to the right-hand side. So 5x to the 7 minus 3x to the 4th equals 0. Do not divide this equation. I know that it's really tempting to divide at this point by x to the 4th because this is what both sides have in common. But if you divide by anything involving x, you always risk dividing by 0 because you don't know what x is, and x could be 0. So don't divide, factor. So what we can factor out is x to the 4th, and what we will have left is 5x cubed minus 3 equals 0. Factoring is powerful because we've turned everything into a product, and the product is equal to 0 if and only if one of the parts is equal to 0. So this immediately allows us to break down the equation into 2 much smaller equations. X to the 4th is 0, or 5x cubed minus 3 is 0. This, taking 4th root of both sides, will produce x equals 0. And then this guy, isolating for x and then take cubic root, will give us x is equal to cube root of 3/5. Okay, so I notice how I have 2 solutions, and then of course they correspond to the 2 intersection points. This is then occurring at 0, that's pretty clear, and the second one happening at x equals cube root of 3/5, that if you wish you can compute as a decimal. So producing a graph here will allow you to see how many solutions to the intersection you expect, and if you did accidentally divide, it will allow you to notice that you're not going to get 0 as a solution, whereas the graph suggests that you should. Let's next take a look at a way to combine functions, and the first one we're going to look at is so-called piecewise functions, where the name is actually very descriptive of what is going on. So here we're asked to sketch the graph of this function. That is x cubed when x is less than or equal to 1, and x squared when x is bigger than 1. So notice that the function is given to me in 2 different pieces depending on what the value of x that I'm trying to plug in is. So in fact, we can say that this is what gives us the function portion, and this is the condition on when that portion of the function is to be actually taken as a part of f of x. Before we start sketching, just to get some idea of how this function works, let's just compute a few function values. So if I'm computing f of 0, that means that x is equal to 0. So I first have to decide which condition does that belong to. Is that less than or equal to 1, or is that greater than 1? Well, 0 is surely less than or equal to 1, which means that I will be taking this portion or this piece of the function and plugging my x into the x cubed part of it. So 0 cubed is just 0. The next one is f of 1, which means that x is equal to 1, and I'm going to have to go through the exact same logic. Is this belonging to the first piece or the second piece? Where does x equal 1 fall into? Which of these conditions? And I can see that in the first piece, it's as x is less than or equal than 1, which means that 1 is in the first top piece of the function, or x cubed. So I will be computing as 1 cubed. F of 2, that means that x is equal to 2. Once again, I have to decide which condition it belongs to. Is 2 less than or equal than 1, or is 2 bigger than 1? Well, 2 is surely bigger than 1, which means that it's the second piece of the function I'm taking. So I'll be plugging 2 into the portion of the function that is x squared. So 2 squared, or 4. If I am to sketch it, I'm going to do it the exact same way, and I'm going to sketch it piece by piece. It is helpful to think about what's going to happen at the connection point. So if I compute x cubed at 1, 1 cubed is 1, and if I compute x squared at 1, although it's not included, just to see how it goes off after that point, 1 squared is also 1. So it means that both of these functions will actually meet at 1. And in fact, one way of drawing it is essentially to sort of dot draw them both and then take the corresponding pieces. Let's try that method. So first of all, I notice that I have a function x cubed, and x cubed has generally this shape. So this is my x cubed. And my second function here is x squared, so a parabola, which means that I'm going to have something like this. And remember that the parabola will lie on top of cubic at first and then below it afterwards. So for small values, higher powers are flatter. Okay, and now the overall function says that I'm going to take the cubic part when x is less than or equal than 1. So my cubic portion of the function is taken when x is less than or equal than 1. And this quadratic portion is taken after 1, when x is greater than 1. So after that, I'm going to switch to the quadratic portion here. Okay, so this is how we can draw piecewise functions. You can also just straight up draw the corresponding pieces. Sometimes they will connect in a nice way like they did here, sometimes they won't. And this is something that you will investigate closer in calculus. Moving on to the next example, let's discuss how one would read information straight from the graph without the formulas. So notice that in none of these graphs I have analytic or formulaic expression of the actual function. So I'm going to read whatever I'm asked about straight from the graph. This is the graph of the function u of x, this is the graph of the function v of x, and this is the graph of the function w of x. Great. So first, u of -1. So whatever goes inside corresponds to the x value, and what I'm trying to compute here will then correspond to the respective y value. So when x is equal to -1, I'm looking for the point on the graph that corresponds to that, which of course is this point right here. And here I don't have a formula, so I'm just going to approximate from the graph. This is, let's say, approximately -1.3. U of 4 means that the x value is 4, so I'm looking for the y value that corresponds on the graph to this x value. It's this point right here. So of course the corresponding y value is 2. Moving on to the next graph, v of 0. So when x is equal to 0, what does the y value equal? 0 corresponds to this point here, so the y value in this case will be -2. When x is 2, y value is 0 from this graph. And then moving on to the graph of w, w of 1, which again means that this is the x value. So when the x is equal to 1, which is right here, I'm going to look up and down my function and decide what it is equal to. Remember that functions are deterministic, so there has to be a unique answer to this. There cannot be two different numbers. So I noticed that this is a hollow point, which means that's not included where that is, but this one is a filled-in point. So my y that corresponds to x equals to 1 is this point at 3. And then finally, y of 2, which is of course x value right here, if I look up and down, I notice that there's only one spot that I'm even close to it, but it's a hollow circle, which means that the function is not defined there. So y of 2 does not exist or is undefined. This next question is asking for the exact opposite of what we've just done. So I'm asked to find the values of x where u of x, so the y value, is equal to 2. Okay, so let me just write in the y value is equal to 2. Y value is equal to 2. I can draw that on my graph. So y value is equal to 2 is, of course, this right here. So it's kind of like your elevator stopped on the second floor, and you're wondering what values of x correspond to that. Here I have this one point right there, which means that x, in this case, is equal to 4. For this next portion, it's asking what are the y values, for what x values are the y values greater or equal than 2. So that means that I am looking for this being y equals to 2. I want y values to be above that. So I'm looking for what are the x values where the graph lies above that line, which in this case, of course, corresponds to this portion of the graph. And that means the x values are from here on. So from here and on to infinity. Notice that I'm allowed to include, or I'm asked to include 2, which means that this point where it is equal to 2 is also going to be included. So in this case, I can say that x's have to be greater or equal than 4. For the next graph here, we have for what x's are the y values on the v graph equal to 0, which of course corresponds, y values equal to 0 corresponds to the x-axis right here, which gives us 3 points right there, okay? And again, I don't have a formula, so I have to approximate it from the graph, so I'm going to approximate them to the best of my ability here, and your approximation might be slightly different than mine, and that's okay. This is just an estimation, so I would say about 0.4, 2, and then 3.7. 0.7, 2, and 3.7. On this last one, again, for what values of x is the y value, the function value, equal to 2? So I have to think of what about this line, this floor, the second floor of the elevator here? Does my graph ever go through that line? Well, there's a hole there, so not here, but there's a point right here where y value is going to be equal to 2. And I can see that that happens just before -1.5. So again, estimating, I'm going to say this is approximately minus 1.4. Excellent. Let's see what the next question is asking. Find the zeros of u of x and find the zeros of v of x. Remember that zeros are also what we call x-intercepts or roots of the function. So this question is simply asking, what about the x-intercepts of those two functions? Because we are given the graphs, it's easier to think of that term as being the x-intercepts. So for u of x, x-intercepts, where does this function intersect the x-axis? And it does so at one point right there, which is approximately, let's say, 0.5. So x is approximately 0.5 here. And the second one is asking for the zeros or x-intercepts of v of x. So when does that intersect the x-axis? And I can see that it's at 3 points here, which of course are the exact same points as the solutions to the equation v of x is equal to 0, which is why they're called zeros of the function in the first place. So I'm going to get the exact same values here as I did in the solution of this equation. So please take a close look at these two things to really understand that these two questions are asking for the exact same information. The other really important concept in functions, and particularly their graphs, are the concepts of domain and range. The domain of the function are all the allowed x values, and the range of the function are all the allowed y values, or all the corresponding y values. Usually, we are more concerned about the domain than range, and range is fairly hard to determine without the graph. Here, we're working with graphs of the functions, so we can talk about both. In a lot of calculus applications, you will concentrate on finding the domain to make sure that you are only using the actual x values that you can be using in the function. So let's take a look at the function given to us by a formula. So y equals x squared. I can draw a really quick sketch of y equals x squared, of course. And remember that this is just a parabola. So for the domain, what are the allowed x values. What x values can I plug in into this equation right here? Or sometimes it's better to ask, are there any x values that I will not be able to plug in into my function? For example, if there's a denominator and I'm not allowed to divide by 0, here there's nothing. No matter what x you give me, I can plug it into here, which means that the domain is all real numbers. The range are all the corresponding or respectful y values. So here is where it's easier to look at the graph and think of what are, again, kind of like the elevator and the floors, what are the allowed or the corresponding y values. Notice that the graph does not exist below the x-axis, because no matter what I plug in into the x value here, it will get squared, which means that the corresponding y values will only be positive, and that is, of course, then the range. Anything greater than or equal to 0, and nothing below it. If the graph is given to me, but the function is not, then I have to read the exact same information, but from the graph. So for example, in the case of this function, for the domain, again, I have to think in terms of x values. So sweeping in the x-axis here and looking at where my function is, are there any points on the x-axis, along the x, that are not going to be included? So I notice that I do have a bunch of holes. At this point here, there's nothing else on this line, which means that x most definitely, at x equals 0, the function is undefined. At x equals 1, there are 2 holes, but there's also a function value defined up there. And at 3, there is a hole, but it's defined down here, which means that the only point that is truly undefined is this point right here, which occurs at x equals 0. So we can say that the domain is all real numbers except for 0, or simply that x is not equal to 0. For the range, we're going to think in terms of all the y values that the function takes on. And notice that nothing is happening below -1 and nothing is happening above +2. And so I am thinking only in between these two values, -1 to 2. And again, thinking like an elevator that rides up, does the function occur at every single floor throughout? We can see that yes, indeed it does. In fact, we can very well see that just this piece alone gives us everything. So I know that my y values are going to be somewhere between -1 or everywhere between -1 and 2. And I just have to think hard about the endpoints. Is the -1 included? Is that a floor that I can land on? No, because this is a hole right there. So this will acquire round bracket. And what about 2? Does my function exist at y equals 2? Well, yes, there is a point that is defined right there, so 2 will in fact be included here. That we've just discussed together, let's list a whole bunch of different things, all concerning this one graph of a function called y equals f of x. Okay, so starting from the top, first of all, we need the domain of f of x. Again, the domain are x values where the function exists. So sweeping along the x-axis, I notice that I have all the possible points between -4 and 4, including the endpoints. So my domain in this case will be x's between -4 and 4. The range are all the possible y values. So sweeping along the y-axis, or thinking in terms of an elevator riding up, I have to think of what are all of the floors the elevator goes along. And again, thinking in terms of this, I can see that it's everything from -3 to 3 in terms of y's, right? From -3 to 3. And the endpoints will be included because the function exists at both of those. So the range is going to be y's from -3 to 3. List the x-intercepts, if any exist. X-intercepts are where the graph intersects the x-axis, which is also, of course, where the y's are 0. So I see 2 points where it intersects the x-axis right here at -2 and 2. So x equals to -2 and 2. And I will note that this is where y is equal to 0. If you give it an algebraic form, that's how you're going to solve for x-intercepts. Y-intercepts is where the graph intersects the y-axis. So I notice that this only happens once here, which of course is because this is actually a function. So for this, we have y equals 3, and I will note that what is true at that point is the x-coordinate is 0. Next question asks, find the zeros of f of x. Again, remember that zeros also means x-intercepts or roots, but we're given the graph, so it's useful to think in terms of x-intercepts, and then I can just refer to above where I found them. So the zeros of f of x are x is equal to -2 and 2. Next up is solving when f of x is less than 0. Less than 0 means the function is negative or below x-axis. So I'm going to have to look at the portions of the functions of this function that lie below the x-axis. And of course, I can see that it's this piece and this piece. I'm going to have to write this in terms of the x values. So I'm looking at an interval here and an interval here. And I can see that my inequality here is strict, so I'm not going to include the endpoints. So altogether, I'm going to have, remember that I'm not actually going to go off to infinity here. My graph is only defined up until -4. So I have that I am below the x-axis between -4 and 2, and then from 2 to 4. Okay, so writing this all together, -4 is included, -2 is not included because I have to be strictly less than 0, and at -2 I'm at 0. Union, so and, from 2 to 4. Similarly, solving for when x is greater or equal than 2, now I am not below x-axis. I'm below this line of y equals to 2. So let me erase what I have so far here. Where is the line y equals 2? It's this line right here. So the question is asking, sorry, not below, above. The question is asking, when am I greater or equal than 2? So when is my function above this line? And I have to give it in terms of x values. So of course it's above this line on this portion right here, which means between this x value and this x value. And I can approximate them to be, again, I'm reading off the graph, so it's not going to be perfect, but it's something like between -1 and 1, and I'm including the endpoints because here, of course, I'm allowed to have x equals to 2. Next up is an equation, an inequality in terms of this function and the function of x squared. Now, the function of x squared isn't even drawn on this graph. So first of all, let's actually put x squared onto the graph. Now, I know that x squared will go through -1 and 1, and it's a parabola. So I'm going to have something that looks like this. So this question is asking, when is the function that is drawn greater, which means higher in terms of y values, than x squared? So comparing these two functions now, on which x values is my black function higher than my blue function? And of course, that is for these values right here. That's when my black function is above my blue portion. Everywhere else, the blue function is above the black. Okay, and once again, I have to classify that in terms of x values. So it's going to be between this point and this point. So that's going to be an approximation, but somewhere between negative, let's say 1.3 and 1.3. And I'm going to include the endpoints because, again, this was included. But this is just an approximation. So let me make it very clear that if you are eyeballing it from the graph, your approximation might be slightly different than mine. Okay, moving along, right along. Next one, we have determine f of 2. F of 2 means the function value at x equals 2. So this point right here, it's the y value of it, which is 0. And then we're asked to solve f of x equals to -3. F of x is my y value, so this is asking for what x values are the y values, is the y value equal to 3, -3. So -3 means this line right here. And then, of course, I see that I have two solutions, this point and this point. So x is equal to -4 and x is equal to 4. Next, find the number of solutions to f of x equals 1. So here I'm not asked to find actual solutions, just how many of them I have. F of x equals to 1. Once again, this means the y value. So it's asking how many times is the y value equal to 1. So I can draw myself a nice line at y equals 1. And I can see that I have 2 points of intersection here and here. So there are 2 solutions to this equation. And I can eyeball them from the graph, but here I'm not actually asked for specific x values. And the last part is asking, when is the function increasing? So remember that increasing corresponded to walking along the function and walking up the hill. So if I am taking a walk on the function, I'm walking uphill up until this point, and then I'm going to be going downhill, which means that the function was increasing on the first region, which means it was increasing between -4 and 0. Here you can include or not include the endpoints. It really depends on even just your book's definition of increasing. Sorry, it's between -4 and 0. Okay, so I'm not going to include the endpoints, because if you're just standing at this point, you're not actually increasing. You're just not decreasing either. Let's talk about algebraic meaning of intercepts. Let's recall once again that a graph of a function is not simply a picture that represents a function. It is a graphical description of the points that make this equation true. So if you pick an x value, plug it into there, what will result is the corresponding y, and the point xy on the graph will be a graphical representation of that one solution to this equation. Because this boils down now to solutions of equations, of course, we can think about them algebraically as well as graphically. In particular, x and y intercepts have very strong both algebraic and geometric meanings. So let's recall how we would describe what x-intercepts and y-intercepts have in common. So for the x-intercepts, we know that the y-coordinate of the point has to be 0. And for the y-intercepts, we know that the x-coordinates of that point, or of those points, have to be 0. So here we have 3 different functions. Let's find the x and y intercepts of each and then sketch a rough graph of each one. So setting x to be equal to 0 is much easier, because that just means plugging x equals to 0, which will immediately result in the corresponding y value. So let's look for the x-intercept first. So x-intercept in this case, I'm going to set x to be 0, which will result in y equals 0 squared minus 2 times 0, or 0. For the x-intercept, I'm going to set y to be 0, which will then result in 0 equals x squared minus 2x. And so now I have to actually solve this equation. Remember, as I mentioned a couple of pages ago, do not divide, because you will lose solutions, but rather factor your equations. If you need more review on how to solve equations, take a look at Module 1 of the Precalculus Refresher course. So factoring out, I'm going to get x minus 2 is equal to 0. And then, as I've said before, the strength in factoring is the fact that we've turned it into a product. A product is only ever 0 if one of the factors is 0. So either x is 0 or this bracket is 0, which it is when x is equal to 2. So I have 2 x-intercepts and 1 y-intercept. So if I were to produce a quick sketch of this function, I can immediately put those 2 points on the graph, and this will guide my graph if I know something, particularly if I know something else about this particular type of function. So my points are x is 0 and y is 0. That's both my x-intercept and my y-intercept. So this point is on my function, and the next point is x equals 2. So this guy right here. This is a quadratic function, degree 2, which means that I know that the graph is going to be a parabola. The coefficient in front of x here is positive, so I know it's a parabola that's going to be looking up. And I know that for a number of reasons, in terms of symmetry of parabolas, it's going to have a vertex right halfway between its roots, so it's going to be a parabola symmetric in between the two roots. There we go. For review of parabolas and other types of particular graphical shapes, take a look at later modules as well. For this next function that we're calling g of x, let's go through a similar process. So what am I going to have here is first, let's compute y-intercepts. Let me just move this out a bit. Let's, for the g function, compute y-intercepts, which once again is setting x to be 0, which will result in 0 squared plus 2, or 2, and x-intercept, which will then set y to be 0, which will force us to solve a solution x squared plus 2 equals 0. I can isolate the x squared here, so x squared is equal to minus 2. Now, of course, I know that nothing squared can ever result in a negative number, which means that this equation has no solutions. That's okay. Not every equation in life has a solution, and this is just one of the ones that doesn't. Which means, this is a very important point to realize here, is that no solutions means there are no x-intercepts. Again, I know that this is a parabola, and I can see that the y-intercept is up at 2. So my graph definitely has this point on it, and it's never allowed to cross the x-axis. Okay? I can also recall, by just looking at the function here, that this plus 2 means that I'm going to take the graph of x squared and raise it up 2 units. So it's going to be simply my parabola x squared, but 2 units up. Okay? And that is, of course, consistent with the fact that I'm not going to have any x-intercepts. For this last graph right here, the exact same type of logic. For y-intercept, I'm going to set x to be 0, which will result in 0 plus 1 squared, or 1. And for the x-intercept, I'm going to solve x plus 1 squared is equal to 0. X plus 1 squared, be careful, the square does not just travel up on top of everything. If you need review of how to deal with exponents, please take a look at module 1. Instead of opening up the brackets fully, I'm actually just going to rewrite the square for what it is, which is x plus 1 multiplied by itself twice. And then the problem kind of reduces to one that we've seen before. If a product of two things is equal to 0, then one of the two things is 0, but they both produce the same root, -1 and -1. Okay, that's okay. That's a repeated root of a quadratic equation here. So if I were to draw this on a graph, that means that a y-intercept is up at 1, so my function will intersect the y-axis up at 1, and it will intersect the x-axis at -1. So at this point right here, and nowhere else. So this is my only allowed x-intercept right here. I'm not allowed to cross the x-axis and come back somewhere else because there's no other x-intercept. It's only intercepting the x-axis here. I know it has to be a parabola because it's, again, degree 2, which means that the only way that I can only cross the x-axis once is if I touch it and not actually cross it. Okay, so my parabola is going to touch the x-axis at this point and go back up. And this is, again, consistent with what we've seen before. This is the whole thing squared, which means that this plus 1, of course, modifies the graph by transitioning it from left to right, a horizontal shift. It's a horizontal shift 1 to the left, and this is what I have here. So in fact, these are the 3 cases for parabolas in general. The parabola can cross the intercept not at all, it can cross it, or sorry, the x-axis not at all, it can cross it once, or it can cross it twice. And that will correspond to the amount of solutions a quadratic equation has. It can have no solutions, a quadratic equation can have 1 solution, or a quadratic equation can have 2 solutions. This is the link between the x-intercepts and what they represent on the graph and the number of solutions to quadratic equations. Okay, so spend a little bit of time to really internalize that, and then please take a look at the exercises that follow this page, as well as the webwork assignment on the module 2 to practice your fluency with graphs a little bit more.